Hi everyone, this is Matt Touchot with Intro Stats, and today we're looking at a problem from my book, Intro to Statistics for Community College Students. This is section 4F, number 30. So section 4F, number 30. So let's read the question together. Hospital wanted to determine if the age of a patient is not related to what part of the hospital they were in. They took a random sample of patients that have visited their hospital and determined both their age and the part of the hospital. The ages were broken up into age groups, and they used a 1% significance level and the Categorical printout below to answer the following, answer the questions above, which is talking about basically running the hypothesis test. So this is what we call a categorical association test. So we're doing a categorical association test. Now in general, this could have been an ANOVA because the type of part of the hospital is categorical, but the age actually is a quantitative variable usually. But you see what they've taken the quantitative variable of age and they've actually just broken it up into age groups. So now we have categorical data. We've basically turned the ages into categorical data. So we have two different categorical data sets that we're trying to see if they're related. So we said in the categorical association test that we're looking for the null hypothesis will be that they are not related. The two categorical variables are not related. So the age of the person is not related or independent of where they go in the hospital. The alternative hypothesis will be that they are related or they're dependent. So the age of the person is related to where they go in the hospital. Okay. All right. It says here they want to determine if the age is not related. So not related, remember, is the null hypothesis. So it sounds like that's going to be our claim. So I'm going to write the null as age is not related to the part of the hospital, and the alternative is age is related to the part of the hospital. And again, the claim was that they're not related or independent of each other. They did tell us it was random data. Since it was a small random sample from a large population, they're probably not going to get people that are related to each other. Our expected counts. Let's check our expected counts. These would be in Categorical, these would be these numbers that are in parentheses. You can see right here where it says expected frequency and it has a parentheses around it. So these numbers with a parentheses, these are the expected counts. And they all look like they are above 5. It looks like the lowest one is right here, 10.76. All of them are above 5, definitely. So it passes the expected counts being above 5. Let's take a look at here's our numbers. This chi-square right here, that's the test statistic. Okay. We have our degrees of freedom as 9. Critical value is 21.666. Our chi-squared test statistic was 34.9. And we have a very small p-value. Now, if you guys remember, this is called scientific notation. Usually that's a good sign in a hypothesis test if your p-value comes out in scientific notation. That means it's really close to 0. This times 10 to the negative 5, remember, just means move the decimal 5 places to the left before you kind of evaluate it. So if I move this decimal 5 places to the left, I'm going to have basically 4 zeros in front of that 6. So 0.0006153 would be the actual p-value. Okay, so again, our chi-squared test statistic was 34.9, so the sum of the averages of the squares of the difference between the observed sample counts and the expected counts are 34.9. Again, does it fall in the tail? Well, the critical value was 21, so if that's where the right tail, remember the categorical association test is a right-tailed test, so the right tail starts at 21.6, we're 34, so we're definitely going to be bigger than 21.6. So our test statistic is going to fall in the right tail. That means the observed counts are significantly different than the expected counts. Our p-value is really, really close to 0.006%. If the null is true, there's a 0.006 probability of getting the sample data or more extreme by sampling variability. Again, that's a very low p-value, definitely lower than our 5% significance level. So if the null was true, this data was unlikely to have occurred by sampling variability. we can reject the null hypothesis. Remember, a low p-value, we're going to reject the null hypothesis. So what's our conclusion? Well, it looks like there is significant evidence to reject the claim that the age group of a patient is not related to the part of the hospital they go to. So again, we rejected the null, and the null was the claim, right? So we're really rejecting the claim. So we're disagreeing with that claim that the part of the hospital is independent of the age. It seems like they are related. Again, a low p-value usually means, in a relationship study, usually indicates some kind of relationship. Okay? All right, so that was number 30 on section 4F. This is Matt Touchot with Intro Stats.